All right, so this morning my presentation is going to be on nature-based solutions, and the title is Wastewater Reclamation and Reuse using Advanced Wastewater Treatment Technologies coupled with MBS. And I'm the National Project Coordinator for the TR Cruise Project, our Reduce, Reuse, and Recycle for Climate Resilience Wastewater Systems in Barbados. So this project is about 50 million US dollars and is being implemented over 5 years, and we're in our third year of implementation. All right, so the all-in presentation, I'm just going to go through a general background, then do the strategy, and then focus mainly on the advanced treatment process. It's a long, extremely long process that's going to take more than 10 minutes, so I'm just going to focus on a narrow section, advanced treatment, then our conclusions, and then the future words for the project. All right, so climate change and water scarcity in the Caribbean region. So water scarcity in the Caribbean region is not a secret anymore. Everybody is clear about it. We have been, on the UN's watch list. You have so many Caribbean countries within the top 50 most water scarce countries in the world. Barbados has been ranked at number 8 to 15 for the past 10 years, and between the years of 2006 up until 2014, we have experienced severe drought conditions. Thus, this is not anything that, Barbadians are, new to. In Barbados, we also had up to in 2022 and 2023 restrictions on water and actually water rationing in some areas. So it's something that we are quite focused on in Barbados when it comes to energy and water security. Because I always say this, you can have all the water that you want. If you don't have a way to distribute it and get it to people, then what is the use of that water, right? So here you can see that UN, the Tribune, a lot of persons have been talking about, the importance of Barbados adapting and mitigating, because I always say there's no more new water available to us unless it comes from space. The water that we have on Earth, that is it, this is it, we got to do what we have. So we need to find a way to recycle, reuse, and of course, reclaim water from wastewater is a solution. Climate change and the changes in our rainfall patterns. I would have just mentioned droughts. I'm just going to bring this a little bit localized to Barbados. The keynote speech this morning was given by my kind of boss, the Prime Minister of Barbados, Mia. So the Barbados Water Authority, or the BWA, and that sits within the Ministry of Water Resources Management, and the minister with that responsibility is the Prime Minister. So this is a project that is country-driven and country-owned, all right? So you can see increase and extreme droughts predicted. You can see drought of immediate concern. And I'm going to highlight the years, 2020, 2020, 2021, 2023, and 2024. So on these trucks here, you can see where trucks actually have to go and deliver water to people. Again, if we have the water and there's no way to distribute it to people, then what is the use of the water? Because people aren't going to be able to use it or receive it. And that just takes us to climate change and water scarcity in Barbados. So you can see here, if you see the chart in the middle here, I'm just going to focus a little bit on numbers. And why is numbers important? Because we're talking about upgrading a wastewater treatment facility to tertiary standards so that we can reuse it for recharging the aquifer and also for irrigation, crop irrigation, right? If you can see here, our raw water quantity as estimated by the BWA in 2024 is about 47 million million meters cubed or cubic meters per year. And the total abstraction altogether is about 62.5 million cubic meters per year. However, if you see here right now, what we have available to us from drinking water that goes to wastewater, in 1966, we had about 11 million cubic meters, and the Bridgetown sewage treatment plant, this is where the project is being implemented, just under 3.5 million cubic meters. So what does that mean? It means that per year, if we're able to recycle that 3.5 million cubic meters of water, we actually have a resource that we can use, all right? And I always say this, if we use potable water for potable purposes, we can therefore if we use non-potable water for non-potable purposes, we therefore reduce the strain on our potable water supply if we only use that potable water for potable purposes. That is when I want to really drive home, because when I pass people driving, my car is very dirty. I just want to say that right now. It's dirty right now parked in Barbados because I try not to wash my car unless it's absolutely necessary, because I don't like to see people have a hose and they just have the hose on and just washing the car for 30 minutes. You can imagine taking a shower for 30 minutes, how much water that is going to be wasted, right? Yeah, 30 minutes. These things happen, right? And when you make these observations, is that how do we change that paradigm? How do we get persons? And someone mentioned this morning, why is this important to me? Why is this important to the next person? It's important because there's no more water. Simply that's it. We talk about drought conditions since 2006. This is 2024. That's a long period of time, right? So, brings us back here now. The potential is that the Bridgestone Solution Plant has the potential to increase or augment our non-potable water supply by at least 4 million cubic meters per year. That's a lot compared to the 11 million, if you look at the top right-hand side, which is we use brackish water reverse osmosis on the spring garden side to produce 11 million cubic meters per year. If we can add 3.5 to that 11, it is a significant increase, but this is step one. There's also the South Coast Solution Plant, and hopefully if this is successful, we can also do this in the south of the island. All right, so the project, this is the Triar Cruise project. I just want to focus on the objectives. So the objectives, of course, is to reuse this water in irrigation and also to recharge our aquifers. And there's a third component that I'm not going to talk about, but we also have a PV or photovoltaic component for the project where we're installing 1 megawatt to offset the cost of pumping this water to the aquifers because we're constructing an 8-kilometer pipeline from the plant to the area where the water is needed by the farmers. I guess I want to go back to this slide because someone would have mentioned AI. So we're also using AI, and the World Economic Forum would have highlighted that Barbados is actually trying its best to utilize data and science to drive policy. So we're talking about science-driven policy. And it's a good thing because at the table you have the policymakers, you have the scientists, you have your youth advocates, you have your various coastal communities and your actors in the area. Why do we say coastal communities? Because at the end of the day, there is going to be effluent that has to be pumped into the ocean. You have to ensure that there is no huge negative impact to the biological diversity. We had a discussion this morning by youth about the coral reefs. We don't want to, augment our non-potable water supply, and then at the other side, pollute the water. So we have to ensure that our treatment process does not have any adverse negative impacts on the environment. Okay, so a lot of information here. I'm just going to focus mainly on the treatment process. So we're going right up to reverse osmosis, but first you go through our microfiltration, ultrafiltration, nanofiltration, and finally our reverse osmosis. Why is this important? We want to ensure that our water is safe. It can be used for human consumption. However, we understand where we are right now, and we're not there yet as a country. However, we have to ensure that should this water come into contact with a human being, that there's no problem, all right? So we're using these processes, and we're going to ensure that you'll see in next slide when we do the design parameters that our pore size is actually 0.5 nanometers, which is perfect for the range because if you can see the left-hand side here, your viruses are removed, your bacteria is removed, also your large salts are removed, and macromolecules and proteins. Okay, so a little bit of engineering from my side because, of course, think about membrane, you have to think about membrane fouling and how are we going to reduce the fouling for the membrane. Membrane fouling is basically, when you pump anything through a membrane, there's some cake formation or some residue that will be left on the film in the membrane. So we have a process where we can actually backwash to remove these contaminants from the membrane so we can actually recycle the membrane itself, right? And we're talking about ceramic and also polymeric membranes to have the pore sizes of 0.5 nanometers. Design parameters, a whole set of design parameters that we went through to ensure that we had a design that is good enough. I'm going to show you what this translates to in the next couple of slides. So by the EPD, which is the Environmental Protection Department, it actually has supersedes the requirements for the UN, the FAO, the Food and Agriculture Organization, and also the World Health Organization. So we had to ensure that we, specifically for our E. coli concentration, that we're under the E. coli concentration, and also our nitrogen, because, of course, nitrogen contributes to eutrophication because of those macronutrients entering the marine environment. And of course, I'm a diver. I like to see nice coral reefs. So of course, we also have at the table our coral reefs activists. So it's a really holistic and inclusive project. Okay, so when we look down here, I just want to highlight again, when we talk about our micro-sieve, so our micro-sieve, the pore size is about that should be millimeters, and then for ultrafiltration, we have 0.02 micrometers. Reverse osmosis, that we get our zero point 0.5 and nanometers in terms of the pore size. The brine that goes back to the environment, the calculations, we are projected to be 1.6 million cubic meters per year. All right. The bottom, these are the models for what we're going to build. This is the third year. Our construction starts next year. And following the design parameters, what was outlined by the EPD, WHO, FAO, and of course the General UN, this is what the plant is going to look like. Currently, we only have up to secondary treatment, which is up to biological treatment. This tertiary steps includes both chemical and physical treatment. Of course, membrane process is a pressure-driven process, so we need a lot of energy, hence why we are using a 1 megawatt PV to offset the cost. And of course, you need our membrane to be chemically inert and also chemically stable enough to ensure there is no negative reactions occurring on the membrane surface or within the membrane, and that could therefore offset or reduce the performance of the membrane. All right, so our last slide and the conclusion. Remember, we started with the objectives. So first objective, second objective, and third objective. First objective, ensure that our treatment levels, level of treatment is able to meet those standards by the FAO, et cetera. And of course, using for agriculture irrigation, I would have mentioned the pipeline 8 kilometers from the treatment site to where the water is actually needed. All right, so these are the things that we're trying as hard as we can to achieve in the next 2 years. Again, we talk about nature-based solutions, and in the secondary treatment process, we have a 5-stage Bardine-Flow process, which has to do with nitrification and denitrification. And then we also have, coupled with our CAS, our conventional activated sludge process, and then we go on to the tertiary process. So we're using nature, basically using microorganisms to digest those nutrients, those macronutrients in the wastewater, and then we do a cycling process where we basically reuse that good bacteria to digest the organics in the wastewater. All right. The final step to ensure that it is safe in case it has to come into contact with human beings, that chlorination step. So we include at the end we have our disinfection, which is our chlorination. So primary treatment, totally physical; secondary treatment, biological; and our tertiary treatment process, physical and chemical. And I just want to say thank you very much. I have to acknowledge obviously the government of Barbados, the Prime Minister's office, the Roof to Reef program, because this $50 million US project is within the general, I can't remember the exact size of the total, 800 million US dollars in all of the things that Barbados wants to do. Is very ambitious, but my Prime Minister. And I also want to acknowledge the ED, Executive Director for the 5Cs, Dr. Colin Young, the CEO of the Barbados Water Authority, Mr. Keith Wright Halliday, and our German counterparts assisting us with the civil works for the design. I'm an environmental engineer, so we need to lean on other persons to assist us with the civil works being done to construct the plant. And thank you very much.